How's everyone doing today? I got a new mic stand. We'll see how this works. Gonna check the levels and make sure they're actually coming through. It looks like they are. All right. So where were we last time? So we got disassembly working. We can look at that real quick. Pop this open in Binary Ninja. And if you're unaware, there's a new Binary Ninja that got released, 2.3. It happened yesterday. We're currently running on the dev channel because we've needed it for a little while, just due to the version of the API that we've been building against. So all these features we've seen, but it's a pretty substantial change. And I think it's the last big change before they release a 3.0. So if you don't have the new one, it might be worth downloading and checking out. I'm doing the automatic update right now, which will pull down the newest nightly, or the newest dev build. I think for right now, we're still going to build against dev, but I'd like to get to the point where, this should build against stable at this point. So there's not really, there's no reason for us not to be doing that. But this looks good. I'm going to open up Chernobyl, which has been the sample program we've been testing this with. And this looks pretty good. We have full disassembly for the most part. It's actually identifying a whole bunch of functions now, which is really nice. Not 100%, but we can go into here and it will start figuring things out. It understands basic blocks. We can switch over to the disassembly graph and go to any of these, and it will give us real basic blocks with a real disassembly graph. The cross references work, which is pretty cool. So I'm gonna head back over to the linear view. If we wanted to go to like a jump, we can see where they go. The data cross references still aren't working yet. So if I look for like a move with a let me go find like a string. That's, I think, the easiest way to show this. Oops, that's not what we wanted to do. This is what we wanted to do. So we can see like these pushes. These cross references don't work, and I'm not sure exactly why. You can click on them and it'll take you there, but they don't pop up. The other thing that's not popping up yet is I don't know how to make the calls show the function name rather than the address here. This is something that we're putting in, so I might just need to manually look up the symbol name and put it in there. But something we can work on maybe today. The big things that I wanted to touch were, we have a broken decoding for one of the instructions, which I think is like a push. Let's see. That's all the stuff I have to do left. We still have this off by ones. I haven't debugged this yet, but we need to build a test harness to actually do that. Something we might do. This instruction right here, the push SR, this is decoding incorrectly, and we need to go figure out why that's decoding incorrectly and fix it. I think it has to do with the operand handling. And the other thing that I wanted to do was redo a little bit the emulated instructions that we've been dealing with. There's the hack we did. We got to open up. We got to open up the new window. Open up this project. So we did this hack to get the length in, where we started saving the length operator, or sorry, the length value as a member, because converting to a emulated instruction from a real instruction is a lossy process. And so one of the things that I want to do is get rid of this stored version and end up saving a copy of the original instruction and then just deferring to that. And that's going to give us the nice benefit of when we want to go back and add in assembling, we're going to be able to assemble back to the original opcode, which or machine code, which we can't necessarily do right now, and we wouldn't know for sure if we did. So I think that that's gonna end up working pretty well, but we'll see how that goes. That might be the first thing we do today, just because I think it's a pretty straightforward fix. And then while we're in here, we'll probably do the push SR2, push SR fix, and maybe we'll build a test harness for just this, which is basically an example program that handles doing like dead code dumping of a binary. So I'm gonna start with creating us a new branch. You know what we really should do is we should copy our git config c users j rosner. I kind of git config best. Did that work? That didn't work. But we do have a git config. Why would that not have worked? That's interesting. Oh, that's really interesting. Let's add global. User.name. Where are we? At least now we'll be able to maybe we can't just do that then. That's fine. All right. Yeah, that worked all right. So yeah, we don't need to go into the Linux version anymore to do this, which is nice. msp430. All right. So we're gonna do defer. So defer non-emulated, and so the first thing we're gonna do is we're gonna replace this with something else. Original, and this is gonna be a so the approach I think I want to take here is basically adding another type. And so this is going to be the original type that we're going to have. Just original. Len equals and so we don't get any nice type verification here. Like we can't control whether or not this is actually type we think it is because it's all a macro, but that should be no problem. The one thing we do need to go do is we need to see, this is the part that's kind of shitty. So right now these don't know anything about like where they come from, and the only place that actually knows that is in here, where we build out the emulation implementation. So we're going to add that dependency back in, which kind of is unfortunate, but at the same time, I think probably is for the best. It means that we don't end up having to do something like this, where we save this as a an instruction. Yeah, so it means we don't have to end up doing it like this. But yeah. So we'll go with this, see if it ends up working out well. The other thing we're going to do is do original self, and it's going to return simple to operand. Does that not work? Why does that not work? Will this compile? I guess it won't compile because none of these have it. Excuse me. We'll get there. Cannot find in scope. I think this is all because it's... Yeah. Okay. So to operand, all of these are going to, where is emulate? So we're gonna end up passing self into all of these. And the one thing we want to make sure, so this is going to end up passing in a reference, which we don't want. I need to see if we're able to basically not pass a reference. We need the receiver of this to turn into not a reference, but itself. And the way we do that is by making this this move it, and that's fine. Normally you wouldn't want to do that because you would lose the reference, but in this case we don't care. I don't know for sure if that will work, but we'll find out. And this change we're doing right now is going to be the same no matter what. And we'll end up passing a reference if we have to, but I don't think we need to. And it's ideal if we don't. Let's get rid of this. And all right, this was the easy one. Let's go to msp430 instruction set, or encoding. And we're going to pick up the... That's not what I wanted. I wanted this. This is going to tell us what our actual instructions are, so I don't have to go through that. So ADC is add C. Move CLR is bic, 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 bic. It's DADD. Dec is sub. Dec D is sub. It's bic, bis, add, zor. What is it not? It's a move. Pop is move. Ret is move. RLA. Add. RLC is add. SBC is sub C. Set C is bis. Bis. Set Z is bis. Let's compare. Oh, you know what? This is move, I think. It is move. Okay. So let's build this. Yeah. We unfortunately need to now do this. Original. Line 37. That needs to be O. Yeah, so this is so I guess the question is, can we do this? And I'm not 100% sure if this will work, but we can find out. RLC ADDC. RLC. Yep, it is right. Okay. I'm gonna turn some lights on real quick. All right, so presumably this works, and we can just recompile everything, and yep, that's fine. Binja. Oh, you know what we didn't do is we didn't run the tests. That all seems to work, which is nice, but we also know we don't have good tests yet for the emulated instructions. Binja And we're going to go to target, debug, and we're going to copy this. So let's see if this all works still. Looks pretty good to me. And we shouldn't be leaking anything, which is nice about this, because we're moving the so I think what's happening here is because we're passing self here, we're gonna move this rather than copy it. So we're gonna store the actual one, the actual value in the structure itself, but we don't have to do a copy because I think we're moving it by doing self here rather than a reference to self. And so that's the ideal situation. Give me 1 second. So this looks good. I'm going to go ahead and we'll go ahead and do this real quick. Rather than store the length, just the length of the offsets are correct. Let's store the actual instruction. Sure that actual instruction when we support assembling only the length, we won't be able to recreate certainty. I probably don't have spell check in here. I don't know if that's how you spell certainty. Certainty, that is right. Okay. The only thing I wanted to change, I think, beyond this is this comment here. We need to store the original clean this up real quick. We need to store the original function because emulation does not keep the original source and destination, which makes it a lossy process. There's certain instructions where the source could use different addressing modes. All right. Let's amend this. Seems good. Oh wow, we really don't get completion on this. So I'm gonna go ahead and push this up. instructions. All right, so that should be pretty much cleaned up now. And the cool thing now is we can return this actual type. So that's the first big thing we wanted to do. Let me go back into here. So this is done. I'm not going to do the test on stream. That seems kind of boring and not a good use of our time here. Let's go ahead and build a test case for the push SR. That's the thing that I wanted to find. It's in here somewhere. I think it's right here. So, that would mean we'll just add it in here for right now, I guess. Push SR. And let's go to, where is it? It's here. Let's just grab one of these because we're going to end up using the same exact format. You know what? We'll just put this in there. There's no reason to bother getting all this sorted out. We already have the infrastructure, and I'm going to look at this test anyway. All right. And it is 12:02. That should be a push. What goes into there? Operand. Register direct. SR is 2, I think. SR is 2. Okay. And so it should have destination operand width. Word. That'll be some. And the original should be a move, I think. What is push? Is push not emulated? Is push? Push is a single operand. All right. Missing source. That's interesting. Oh, that's so strange. I'm gonna switch over here real quick. I gotta log into microcorruption. I want to do it while I'm not logging into stuff on stream. All right, we're logged in. So this is at what? It's at 4CF0. Yeah, so it's doing push SR. 0212. So this is what it looks like. Let's decode this manually and get all the values. Actually, it's that because we're a little endian. All right. So we got 0001, which makes sense. 00100. Okay. And then BW is going to be 0 because it's 16-bit. AS will be our last two, which is 00. I guess this might be wrong because we don't have a 00 here for these, at least for SR. So 00 for SR must be a special case. Instruction. That's not what I wanted. I want this, I think. One, two, three, 4, 5, 6, 7. These are all 7 addressing modes. This doesn't specify so I want to be able to compare this. Zero one is indexed, 1 0. So 0 1. So this is when PC is used. But it doesn't tell you the conditions for when it's used. Like this we know is I'm afraid that we did this in a way that's not going to be compatible with what actually is real. No, we did okay. Okay. 2. So if the source... No, we did it backwards. But we might be able to still salvage this. I really don't want to have to like invert the logic on this and do source first, but that might end up being the easier way to do this. RISC mode. Normal effects of the addressing modes. The addressing modes using PC as a working register use the normal effects of the addressing modes. The special addressing modes are caused by pointing of the PC to the ROM word following the currently executed instruction. Zero. One and 3. Yeah, so it seems like this actually would be the correct thing to do, would be to have so 0, 0 and 1, 0, so 2. So 0 and 2 respond with the normal expected behavior, which means we might want to go back and do the source, which is unfortunate. All right, let's... Okay. 0, 1, 2, 3. Unreachable. So if the register is I guess if it's here, it's always the same thing. We don't have anything special. Okay. So if it's 3, if it's 1, there's 3 different conditions based on the register. Match register. And that ends up being, if it's register 0, if it is register zero, 2, and 3. Zero, has it been a fun side project or more annoying than it's worth? It's been fun. I mean, I haven't written Rust in a while, and so jumping back into this has been good. I also see this as an opportunity to improve the tool, which is something I've been wanting to do, and learn how to build plugins. Like, this itself, this plugin, is not going to be super useful probably to me in the long term, but after doing this, I now know how to do this, and there are many other plugins that are going to be useful. I'm also taking an opportunity to improve the documentation for the API, which means that when I need to do this again or someone else does, it will be better. And so I'm kind of hoping that ends up making the community still a lot stronger, and we get better like language bindings for Rust. We get better documentation. We get better plugins, and hopefully other people will build stuff that is useful to me, and maybe people will find this useful for them. So yeah, I mean, it's about the struggle, and it's a fun project, and I'm learning a lot about how to do things well, not so well. Let's see. So we go back to here, and so we have regular registers here. We got PC. Oh, there are 4. Okay, so 0, 2, 3, and then. Let's see. That's not what I wanted. That's what I wanted. And then 1 or 4 to 15. And then invalid source. U16 and U8. So source and register. All right, we're getting a little bit closer. So if we are register 0, source 1. This is what we want. Now, if we are source 1, register 2. I wonder if all of these cases there's going to end up being a second word and we can just abstract it out. So this is source 1, register 2. Did we grab the wrong one? Oh, register 3. Register 3. Register 3, source is... Register 3, source is... Source is 1. And then what is this? This is source 1, register 1. And I think we have really good tests for this. So I think we'll be okay. And we're not going to have problems with verifying that we have the right stuff here. All right. So source 2. Is there more than one implementation there? Looks like there's not one here. There is for R2 and there is for R3. Batch register. So we said that there is one for 2. There's one for 3. And then there is 0 to 1 or 4 to 15. And otherwise, it is a decode error. All right, so if it's source 2, register 2. Register 2, source 2 is just this constant. Then source 2, register 3. Then other registers with source 2. Other registers. All right. Then we have source 3. We have source is 3, which we have a special case. So we have one for basically all of the non-special cases. We have one for PC. We have one for SR and one for CG. Right. Match register. So 0 gets its own. 2 gets its own. 3 gets its own. And then 1 or 4 to 15. And everything else just gets this error. So if you're register 0 and source 3. If you are register 2 and source 3, is it constant? And this is also a constant, this next one. This is what, register 3, source 3? Then, what is this? This is just auto increment right here. One, two, 3, 4, 5. I think we're missing a constant. So it's 4, 8, 0, 1, 2, -1. So 1, 4, 2, 8, -1. We're missing 0. What's the constant 0? So that's source 0, register 3. Source 0, register 3. Oh, yep. Register. Zero, register 3. So 0 to 2 or 4 to 15. And then let's just grab one of these. All right. All right, so that should be correct and give us basically what we want. We should be able to run cargo test and have it spit out tests passing. Hey, odd 1233. It's a good language. I've been pretty happy with it. It's kind of difficult to learn if you're not super familiar with writing safe C already or C++. But like once you get down that, it's not bad. All right, we have one failed test, and it's still the same test, which is interesting. I I didn't do something dumb like put this in backwards, did I? Just real quick. Yep, there we go. I did put it in backwards. All right. So, I think we're pretty good. I'm going to go ahead and I'm going to rebuild this. And we're going to kill this. And we are going to drop that in there and we'll restart it by Ninja. All right. Now, where is that part that was failing? That's a pop SR. That's interesting. It didn't break it here. I wish I knew where the instruction was. I don't remember where. Yeah, this is it right here, I think. So it's decoding now properly. Those are the bytes for the instruction. So we're getting better. The other thing, I guess, is do we need to fix the destination parsing? I think that the destination parsing is correct. Yeah, so this one actually, we did source only because it was all that was needed. I think that this is correct. I guess with the benefit of this being a little bit more accurate, which is nice. Actually, I'm going to do it from here because I don't know what's set up in this. All right. Fix. Operand decoding. I'm going to get the URL. Decoding table. Decoding. We're not complete. Some instructions not correct. So decoding that were valid. Sorry. So let's go back to here. So that's fixed. So let's figure out now our negative problem. We need to figure out whether or not our negative values are being decoded incorrectly, being translated incorrectly, or being displayed incorrectly by Binary Ninja. I was thinking about building a program that would just give us a dead code listing, but I'm thinking about not wanting to do that more and more. One of the things we can do is we can grab some of the instructions here and we can find one that is being used incorrectly, and we can grab the bytes and we can see what it decodes to. And that'll tell us real quick if we have a problem in our decoding, a problem in our translating from the bit representation to the numerical value, or whether what we're passing in the text token we're passing into Binary Ninja is just wrong. So I'm going to go ahead and move over to here just so we can find an instruction that we know is wrong. To start with, I am going to look for what the errors are that we're seeing. It looks like it's for move instructions with a negative value. So let's go ahead and look through here. So this, I think, is what we're gonna probably be able to use. This is at 4462, 44. Yeah, so if we look here, we see that it's move SP. This is negative 16 off of R4, and this is negative 15 off of R4. So we're off by 1. Let's see here. So these are the bytes that we want. Let's see, we're going to copy that. So the question is, do we even care about doing this manually, or should we just go in and write a test? I guess we can do this manually first. What is this? So 4184 FF0F. You know what? I think it actually is F0FF. Let me grab this. This is correct here, at least. Let's see. That's fine. So this is a move instruction. So 0, 1, 0, 0. 0, 1, 0, 0. SP is 2. 1. 1. 8184. 8441. That's it. Okay. All right. So that is the instruction. And then we do 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So this is our operand. So we don't really care about any of that. We just know R4 is our register, and that's fine. We know that this is the number we care about, and this ends up being 1, 2, 3, 4, 1, 2, 3, 4. That is the That's so weird. Because it should be a 16-bit number. Are you asking what this is right here? So this is an online war game. So basically like learning security concepts. And it's based around the msp430 architecture, which is a microcontroller architecture created by TI. And it's basically an introduction to binary exploitation, so basics of reverse engineering, basics of memory corruption, and building exploits against that kind of system. So this is basically a disassembler and debugger that is in a web interface. So these are your registers up here. This is the current instruction that's being executed. This is how you interact with it. So IO console, so anything that it's printing or requesting from us. This is the memory. So this shows us the address here, and then the actual memory contents. And then this is the actual disassembly, instruction by instruction. Yeah, no problem. And if you have questions, definitely feel free to ask. I'm happy to go over this. We haven't played a lot of this recently because I've been mostly focused on building the implementation of this for Binary Ninja. But the game we're almost done with. I think we have 2 levels left. This one right here that I'm looking at is one of the ones that we're doing. And it just seems like it's a good opportunity to grab code from here so we can verify that we're disassembling correctly, because we have something we can match it up with. F0. Oh, because I did this wrong. F0. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So if we swap this and make it the right value, this ends up being 15. Right? Yeah. Wait a minute. Is this a bug in there? Yeah. This is 15. It's F. Why? Are they representing it as 2's complement? Although, so that's the weird thing. So msp430 is one's complement. But you wouldn't do 15. You wouldn't do 15. No, look, it's 16 bytes. Because it's 0. Hold up. It doesn't specify one's complement. That's really weird. I mean, I guess we can break here. I don't know what it's in printf, so we can hit that. Reset. Continue. Access Joe 1, 2, 3, 4. We can verify what this is. Hey everyone joining, welcome to the stream. We're just going through some microcorruption and building a disassembler. Feel free to ask any questions if you have them. I'm happy to kind of go over what we're doing. Right now we are looking into why the representation right here doesn't match up with what we are getting right here. And the question I have is whether or not it truly is using one's complement or it's using two's complement, because the format of this, so, I mean, we were told it's one's complement, but the format of this seems that this would be wrong. So we're debugging. We're gonna go and look at the memory right now, and we're gonna see what is in here. So if we look at R4, R4 is 3D E4. Uh, 3D E4 minus so 3D D4. So 3D D4. That would be 0, 1, 2, 3, 4. Move the stack pointer. So for sure, like that is, it is 16 and not 15. If we go back and we make this just like F, which is 15, 3D, D5, D0, 1, 2, 3, yeah. So why? Is it actually 2's complement? Like, that seems right. Negative numbers. It is stored in 2's complement. Why did we think that they're using 1's complement? Huh. So, depending on the... Do you know what 1's complement and 2's complement are? Because I guess it probably makes sense to start there if you don't. Yeah, so 1's complement is just an inversion, whereas 2's complement is an inversion plus you add 1 to the value. So some architectures will use 1's complement, and what it means, and in both cases, the most significant bit right here, this one is used to denote a negative number. So in this case, it knows that this is negative because the most significant bit is unknown, is 1. So in 1's complement, I think it's in 1 or 2's complement, you end up having a like a negative 0, positive 0, and I think it's 1's complement does, and it ends up solving like some of that by doing 2's complement, but it works effectively the same way. The most significant bit determines whether it's negative or positive, and it does the same sort of thing. You just don't add the 1. But if that's the case, that would explain why like a whole bunch of this math is kind of wonky. Why did we think it's 1's complement? I mean, let's go find another negative number. I guess a jump would be probably the best. That's not going back. That's going backwards. Okay. So I mean, we can look at this one now. What is this? This is 2-3 FA. A is 8, 9, A. And if we go and look at a jump, what is this? This is JNZ. So 0, 0, 0, 1, 0, 0. Wait, what? 2-3 FA. Did I miss a... 0, 0, 1, 0, 0, 0. And then this is our number. So 0, 0, 0, 2, 3, 4. So it ends up being that, which is 4, 5, 6. So if we look here, it's going to go 1, 2, 3, 4, 5, 6. Okay. That makes sense, and it's why our jump logic is so weird. All right. Cool. So, ones complement. Basically, we can get rid of the ones complement, like everywhere. Expected. This ends up being an I-16. Oh. Nope. Actually, these are fine. Absolute. Shit. So I hope that this is going to work and do the conversion for us. So a whole bunch of these are failing now. Which is fine. It also means that our jump instruction code is wrong. And it means that this logic can get changed as well. So we have 10 bits here, and we are going to need to turn this into 16 bits, basically. So if bit 10 is oh. JXX fix offset. I think that's it. Basically, we just need to set the end of the bits, and no, it's an OR. And we don't want this. We only want the front bits. 1, 2, 3, 4, 5, 6. So what is the first 6 bits? That ends up being F2. 1, 2, 3, 4. Eight, 9A, BC. I think that ends up giving us the right value. And then this ends up meaning that our jump logic gets significantly easier. Like we have all this crazy logic in here for jumps. Offset absolute. Like, I don't think that this even is needed anymore. Oh, no. Well, it may not be. Because we can use PC relative, I think, as the type. But this +2 gets to go away. We'll see that. So, handful of failed tests. Let's go to here. And basically, we gotta just go fix all these. So operand 389. For 3. Indexed. That's line 344. Uh, 239. And then 938. And that is 260. all these tests are going to end up being kind of weird now because they're using odd numbers, which you wouldn't actually see. But it is what it is. I don't care about going in and modifying the bytes at this point. It's 573. Uh, 658. 469. And then 381. I wish I had realized this when we were doing the jump instructions, because we had to do all that crazy logic, and it makes total sense now, like why that was all off by 1. 547. Okay, our tests pass. And if we go back to Binja, we can get rid of offset to absolute, I think. Because it's... Is it the same? Yeah. Why is this different? Oh. It ends up being the same thing. So that should just work. Let's go ahead and discard that. We also need to copy this over first. Let's see if these all line up correctly like we think they do. Reload. Okay. That looks good. It's looking for like negative numbers and jumps. So this is off. And then, what's this, 4422? 4416. Yeah, so actually we need to fix one small thing, which is in here, we just need to add Wait, offset is I64. We need to... This might be the correct... no implementation. All right. Yeah, these are both I64. All right. Let's kill this. Let's copy that over. And this should give us what I think will be the right value. So correct -1 there. Look at our first jump. And we need to add it's 2 because a jump instruction is 2 and not 1. All right. So let's go back to here. We have 4424, 4416. 4438, 442C. Yeah, so these are all correct. So that makes sense. We fixed our negative issues. We can go to here and get rid of that. Lots of clippy stuff, but that's fine. Negation by multiplying. All right. Logic. msp430 doesn't actually use ones complement two's complement behavior divided by rest. All right, so we have fixed our off by 1. Actually, we should go verify that first of all. Where's that move? Yeah, it's right there. So that's correct. You know what we didn't do? Yeah, that's fine. So what changed here? We're gonna skip that. Skip. Nope. Nope. Yep. Add +2 to adder to get past the jump instruction. Fixed jump logic. Correct to formatting fixes. So this all seems pretty good. I think in terms of correctness, I think we're here. There's still a few things that aren't working right. Like it's not correctly identifying the calling conventions a lot of the time, and I don't see any registers showing up when it does correctly identify it. And so I'm not sure if there's something we got to do differently for that. It's possible. Or if it just happens to be that, oh, that's weird. Yeah, that's weird. Why does it have these here? Yeah, I'm not sure. Anyway, I think I'm gonna wrap it up for here tonight. I think we got most of the work we wanted to get done. All of the outstanding like bugs I think are basically fixed. This isn't a bug; it's just a correctness thing, and I'm not sure if we are correct right now. I need to go verify. We don't care about one's complement because we're not using it. I still don't know what that is. But yeah, I think that I'm going to do some refactoring of this off stream, and we will basically get the plugin into a state where we can start like filling in the rest of the parts of it. And yeah, I mean, like it works, but it's just kind of like gross and not well structured. We still need to do the flags that was going to get implemented, and then we still need to do the lifting, none of which is done yet either. But yeah, probably this weekend or next week we'll pick that up, and we can start finishing up and getting this like fully functional. Once the lifting and everything is done, the last piece is maybe to add assembling functionality, and the back end of the assembler is actually going to be really, really easy because of the way that this is all set up. Like we just have to basically create a trait for assemble, and then implement assemble for all of these, and it's just pretty straightforward packing of the bits. The front end of it I think is going to be a lot more difficult because we're going to have to basically build a parser for it and do a bunch of like magic, especially because I don't know how you would specify like your relative jumps and stuff without like a real address. But yeah, that probably is gonna be the next most difficult part after the lifting. Anyway, have a great night, everyone. Hope you enjoy it, and we'll be back probably in a few more days, and we can pick up where we left off. Good night.